Let's talk about the MongoDB assignment. Okay. So what we're going to do is for the MongoDB assignment, we're going to keep going with the university toy example. Right, we started at the beginning of the semester. We're going to just keep adding to this. And so we're going to model some of the classes that are on the right-hand side of this class diagram. We're going to model being able to have students take a quiz online, right, and be able to provide answers to multiple questions, right? So and the questions, they're going to be different types of questions. They're going to be multiple choice questions, true, false questions, and there's going to be several things that we need to model. We need to model the student. We need to model the types of questions that we have. There's an inheritance relationship here with a base class question, and then a couple of subclasses, multiple choice and true, false, that inherit from questions. There's a many-to-many relationship between student and answers, where a student can answer many questions, and a question can be answered by many students. There's quite a few other things that can be modeled here, but that's going to be the focus of the assignment. There's a couple other things that we're going to be playing around here in class. We're going to practice with modeling these other relationships, like student to section, right? Where you have multiple enrollments, a student can enroll in many sections, and sections can have many students enroll in that section. You can have there's also an inheritance relationship here between a base class of user and a subclass of faculty inheriting all the features of the student, of the user. There's a couple of one-to-many relationships, right? Here's an aggregate where a faculty can author many courses, or faculty can teach many courses, but there's no life cycle dependency, right? If the faculty goes away, right, the section still can be taken by some other faculty. But there's a composite relationship between courses and section, right? If the course doesn't exist anymore, then there's no point in having a section for that course, right? So we'll see how we go about modeling these kinds of things, right? We already looked at how to do it in a relational database, right? Using cascade deletes and having mapping tables or association tables. And so we'd like to see how we would do the same, how we would model and implement these kinds of things, but in a non-relational database, right? So in class we'll take a look at this left-hand side of the class diagram, but for the assignment, you get to practice it modeling the right-hand side of this class diagram. Okay. So you're asked to create a couple of JavaScript files, and we're gonna to implement this connection to a non-relational database. We're going to be using a Node.js. Node.js is a JavaScript interpreter that allows you to execute JavaScript on the command line. Very much like we've been using Java and JDBC and JPA as our framework for interacting with relational databases. We could have just stuck to Java to connect to Mongo. That's fine. The thing is that because the data that is going to be stored in a lot of these non-relational databases, a lot of it is formatted in the JSON format. It makes sense to work in a language where JSON is the native data format. So we're going to be using Node.js as our interpreter to run our code. And so we're going to be writing a code to connect to MongoDB using this is an example code to connect either to a local MongoDB or a remote database, right? So you should have a local MongoDB running on your local machine where you do all your implementation. But once you feel confident that it's working right, you would deploy this into a remote server, right? So that our TAs can create and run this remotely from their machines. Here's an example of how you would go about doing this. Depending on where you deploy this on AWS or Heroku or wherever you deploy it, the best practice is to have environment variables that keep track of your usernames and passwords and URL connections. And this is true for in any environment. Even now in your relational databases, right? you should not be hard coding any of your username and passwords in your source. Instead, you typically use it either in a properties file or even better yet in an environment variables that are not even in any source code, right? And they're read dynamically at runtime. Here's an example on how you would go about doing that. First, we're going to ask you to create schemas that represent the data structure of some of the things that we're going to be modeling. So we're going to be modeling the students. We're going to be modeling the different types of questions, multiple choice questions, true, false questions. It's best practice to have schema files implemented in separate dedicated files, JavaScript files. One of the things that we're going to learn about MongoDB is that it uses an elastic schema, meaning it does not enforce any schema, right? Unlike relational databases where you have to declare all your schema a priori, right? You have to create the tables, and you have to say what fields are what data types, right? There's an ID is an integer, and first name is a bar chart, and whatnot, and then all inserts and updates are validated against your schema, right? In non-relational databases, in MongoDB in particular, it is optional. It's not enforced, right? So the schema can grow and change and over time, right? So it does not enforce any validation whatsoever. It has its pros and cons. For those of us that come from relational databases, this it's something to cringe at. What do you mean you don't have a schema? You have to first define the schema, right? And the relationships and the enforce all the constraints of how the data structure is implemented. Not so in Mongo. It's not enforced, right? Instead, to recoup some of that we've learned about relational databases and creating the schema and validation and all of that, that's going to fall on the application server, right? At the source code. The source code, we're going to write code, right? That's going to do the validation for us at the application layer as opposed to the database layer, right? Already in our implementation with relational databases, we already do a lot of validation at several stages of the application, right? Usually, you do validation at the front end, right? And typically by providing a good user interface that minimizes or discourages the inputting bad data, right? By providing maybe drop downs and checkboxes and radio buttons so that it minimizes the chances of me submitting something that is of the wrong data types. Yes. So there's a lot of validation at the front end. There's also again at the middle tier, right? Usually at the server level, where you have all your Java, all your classes. That's another layer of validation, right? Because you have to instantiate these classes, and these classes won't instantiate unless you have all the right data types. Yes. And once you have all that in memory in your code already instantiated and everything ready to go, then you do you pass it over to the relational the data layer to store it permanently in the database, right? Where there is another layer of validation, right? Where the database will check that things are dates and integers and bar charts, the right sizes and whatnot. Yes. So usually the mantra is that you validate as early as possible and as often as possible. Right? So there's validation all around everywhere in the application. So here's where we're going to do a lot of the validation by implementing the schemas at the application level. Right? We'll declare the structure of our data using JavaScript and say what are the structure of the data here in these files. We'll also look at how to implement inheritance using non-relational databases. In particular, we'll create a base class question that keeps track of all the data that is common across all questions. So all questions have maybe a title, a description, what the question is, how many points it is, right? But then you have special types of questions, right, that have specific features, right? You have true, false, multiple choice, fill in the blanks. Each one has its own little nuances on how to implement that question. Yes. So we'll implement those types of questions, right, as a base class question schema, and then several question types that inherit from the base class question. So here's an example on creating the schemas, on creating the question schema. We'll note a couple things here. One of the things that we'll point out as we go and do the demo later on is that we're declaring the primary key here. The underscore ID is the default name for the primary key in Mongo. And usually the underscore ID for the primary key usually is left to the database to calculate for us, right? Very much like we do auto increment in a relational database. Yes. Here we're going to override that. We're going to say no. We're not going to let the database do that for us. Instead, we want to own that. We want to own that. We're going to declare it as a number. Usually it's some hexadecimal number, really big hexadecimal number. But here we're going to own that because we want to generate that ourselves. A couple other things here. We're declaring questions. The actual question for the question is a string. How many points? Here is a question type. This is using the denormalized strategy, right? Where we have a discriminator field that tells us what type is the base class, right? So that we can pose as one type of question or pose as a different type of question, right? In a non-relational database in Mongo, we're only going to use that strategy, right? The denormalized strategy. Remember that in relational database, JPA allowed us to implement 3 different strategies, right? There's no equivalent here. We would have to implement this from scratch, and this is the strategy that we're going to be using in this assignment, the denormalized implementation. So we have the discriminator field here, what type, and then we have 2 embedded data types here. We have the multiple choice and the true false questions. Notice that they are not primitive data types, right? See that? So this is using a strategy called the embedded data type, right? Where you can have an object embedded inside of another object, okay? Which is something new, right? We can't do that in relational databases, right? In relational databases, the only way to embed something is really through foreign key, primary key, right? Where you can only refer to other objects, yes, and where you point from a foreign key, you point to some primary key of some object stored in a different record, yes. So there's no equivalence of this in a relational database unless you perhaps want to consider blobs, right? Binary objects stored in a field. Then yes, there is an equivalent. But typically, we don't store things like that. But here, since JSON, the JSON format is an object format, right? We can have objects embedded inside of other objects, right? We can have arrays of objects, objects of arrays, arrays of objects. So it could be arbitrarily complex, right? This object that we're storing in the database, yes? As opposed to relational databases where are just flat, which is just a table, right? And each record is all you get. You don't have a record that would have fields inside of that record, yes? Here you can. A field can be some fairly complex additional object. So multiple choice. Here we're using what is called the embedded strategy, so embedded object strategy. So an object that contains other objects, and this object can contain other objects, right, indefinitely. Now this is also considered denormalized, right? As opposed to, if you remember normalization, the strategy is to split the data into multiple tables, right? With the intent of avoiding redundancy, right, and repetition, so that we're avoiding the risk of inconsistency, right, where you would have information that is stored multiple times, right, in different portions of the data set, right, and they might drift, even though logically they should have the same values, right, they might, since there's no way of enforcing the uniqueness, right, they might drift apart from each other, even though logically they should be the same, right? So same thing here, right? We have this multiple choice here when you embed data, right? Imagine this were a client or maybe a customer, and the customer might have an address embedded in here, right? And imagine that you have customers that are family and they live in the same address, right? And that object can contain, the street name and the state and the country, blah, 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 and the zip code, right? It could be that if you use an embedded object, and we are two different customers, but we are family and live in at the same address, logically our addresses would have to be the same. Yes? Right? But if you are embedding one copy of my address under my record and one copy of the address under your record, right? There is the risk that even though logically those addresses have to be the same, right? Since there's no way to enforce it, it could be very easily that those addresses drift apart from each other, right? Because maybe I misspelled the street name, right? I missed an S somewhere, right? And there's no way to enforce the uniqueness there. Yes. So this too is considered to be a denormalized strategy. Only if you can enforce the fact that there's not going to be any repetition, okay? Then it's okay, right? Or if it's okay for these to drift apart, that's fine too. It could be that in this quiz, yes, it was the same question, the same multiple question, and in this other quiz, I reused the same multiple question, but it's okay for me to change the question here for this quiz and change it for this other quiz, to change it, yes? And then if it's logically okay for them to be separate, then the denormalized strategy works fine. Okay, but if you know that you're repeating data, that logic has to be the same, then you would avoid this strategy. Instead, you would have a foreign key here that would point to some other record that would live in some other collection. Make sense? So there's definitely the choice of embedding data or splitting it up into separate collections. Now, as much as possible, it is a best practice, whenever possible, if you can avoid redundancy, if you can avoid inconsistency, preferably the embedded strategy is preferred. Right? It's preferred for performance purposes, for storage, for indexing, in general. It performs better when you can denormalize. For performance, even also in relational databases, same thing, right? Usually, when you can denormalize by using materialized views or views in general, right? You can improve performance, but obviously you run into the perhaps risk of inconsistency. But if you have materialized views, you can have best of both worlds. Right? You can have the denormalized schema, but also avoid inconsistencies, right? Anyway, so it's preferred to use the embedded strategy. Then here we have a quiz. The quiz schema. This quiz schema is going to contain an array of questions. Right. So notice that here we have an array, and the object that is contained here for each question is going to be an array of foreign keys. An array of foreign keys. Right. The data type is going to be object ID. That is what the equivalent in MongoDB as a foreign key, right? Where I have the ID and the unique identifier of some other record, okay? And it's pointing to objects of type question model, and we'll see what that means in a minute. Okay? We also are configuring where in MongoDB we want to store this. Here we talk about collections as opposed to tables. Collections are the equivalent of tables in MongoDB. So we're going to be learning a new jargon, right, instead of terms, right? But they are equivalents in both worlds, right? Same thing. We don't talk about records. We talk about documents, right? We say that MongoDB is a document-based database, right? It stores documents, right? And then you can store a document, then you can retrieve documents, and these documents are formatted in JSON. Right, are formatted in JSON. So you store a JSON document and then you retrieve it from the file. You can also think of it as an object database, right? You're storing objects, right? And then when you retrieve these objects from the file system, you do a pattern match. You're saying, well, find me all the objects that have this pattern, right? You have these values for these fields within these ranges, and then it retrieves an array, a collection of all the records, all the documents that match that criteria of the pattern that you're looking for. All right, so there we go. So we're gonna practice the two strategies, the embedded object strategy, and we're gonna use also practice also the the reference strategy, right, where we can store data in separate collections, and they can reference each other. Okay. Also, another thing that to point out here is that usually when we think about foreign keys and primary keys in relational databases, we think of the data is split up into multiple tables, right? You have the addresses over here, we have the clients over there, we have the orders over there, right? And the records are spread out over multiple tables, right? And when you want to reconstruct the data, you need to do a lot of joins, right? We have to join the records in this table with the records in this table, with those records of some other table, and then you reconstruct using a select, and the join and whatnot, right? And then you come up with a result set that has data from several tables. Yes, the fields that you care here. Well, in non-relational databases, or in Mongo in particular, there's no such thing as a join. Right? There is no join. There's an algorithmic equivalence of it, which is somewhat like a group or like an aggregate function, right? That will literally will iterate, right? And looking for this reference, and will iterate the other collection, looking for the records that match your reference, right? Obviously, trying to optimize using indexing and whatnot, right? But it's at the application level, right? As opposed to in a relational database, you kind of think of it delegating it to the database to do all this joining. Yes, here is it's going to be done at the application level. Here, the many-to-many, we're also going to have a chance to play around with many-to-many. We'll create an answer schema that's going to allow us to keep track of answers that multiple students have answered, right? So we're going to have a question, we have a student, and a student can create many answers, right, to a whole bunch of questions. Right? So if you look at it from the student's point of view, they have created many answers, right, to a whole bunch of questions on the other side. Yes. If you look at it from the question side, right, you could say that all those answers were made from multiple students for the same answer, for the same question. Right, so a student can generate many answers, and from the question side, one question can have many answers from multiple students. So it's a many-to-many relationship, right? Now, in both cases, because it's usually you want to think about many-to-many relationships as bidirectional. Usually, you like to be able to say, answer from the student's question, from the student's point of view, where it says, well, what are all my answers? Right? I want to see a list of all my answers. But you can also be able to, you should be able to look at it from the question's point of view. It says, what are all the answers for this question? Right? And so that brings a challenge, right, on how do you implement it. If it were a one-to-many relationship, that's easy, right? You could just have the student, if it's only one directional, usually what you just do is easily, in MongoDB, you could say, hey student, you can have an array of all the answers that you've created, right? Go to something novel here, right? We don't have the equivalent in a relational database of having a field that can contain multiple foreign keys. Right? Usually in a relational database, we have a field that has a foreign key, and that's it. It's just one foreign key in that field. Yes? Here, instead, we can have an array of foreign keys, which is pretty cool. Right? Now, the UML class diagram, where you have here A here, and you have B, and you have one-to-many, right? Usually the way to implement this in a relational database is that on the many side, you have foreign keys pointing to the parent. Right? That's the only way to implement it. But now in a non-relational database, instead of implementing it this way, we can have an array here, right, of foreign keys, and say now the parent can have all the foreign keys, B1, B2, B3. You're referencing all the records on the other side, right? You still have the classical way of implementing it, right? Where the child has a single foreign key pointing to the parent. You can still do that in a non-relational database, MongoDB. But now you have the option of instead doing it the other way, right? Where the parent has an array of foreign keys to the children. That's new, right? So that's another alternative that's going to open up for us that was not available in relational databases, right? But now here in the decision to go one way or another, right, might be somewhat trivial. It says, well, I could go either way. That's fine. But when you add the fact that where you have many to many, where you have A and B, right? You have many to many. Now you have now you have choices here, right? Where you have in both cases you could have A array of pointing to multiple B's, yes, right, and B having multiple pointers to A, right? And notice that if it's bidirectional, this adds the challenge that there could be some inconsistency, right? That if I answer this question, right, I definitely have to have a pointer from A going to B because I answered it. So I need to reference it and say, okay, that's my answer. But then that means that on the other side, you have to also have the same pointer pointing back. Otherwise, there would be an inconsistency, right? If I say, I am enrolled in this section, so now the students can have an array of sections that they're enrolled in, yes? Now, if you look at it from the sections point of view, you would see, well, what students are enrolled here? You should have also the same array, the same student has to be represented from the sections point of view. Now you have two updates that you have to maintain. If you enroll a student in a section, you have to point from the student to the section, and then point from the section back to the student. See that? Because you have to update in two places, this adds the risk of inconsistency, right? Where maybe you update one but not the other, and depending on how you query it, you might get two different answers. Right? How come if I see it from the student, I am enrolled, but if I see it from the sections, it doesn't show that the student is enrolled? It would be an inconsistency, right? So this adds some complexity. Oftentimes, if that's the case, right? If that's the case, then it's better to go with the classical implementation where you have an intermediate mapping table or mapping collection that has arrays going both ways, right? Saying that there's only one place that shows that this student is enrolled in that section. I'm not updating two different places. It's only one representation. So depending on what you're doing, right, and depending on what the use cases are, you would choose one versus another. Make sense? Okay. In this case, just for us to play around with we're going to go with the normalized implementation. Right, we're going to have an answer, and in the answer, the answer is going to be a mapping collection. Right, it's going to point to. Notice it's going to use a reference. So it's referencing the student. It's referencing the question. Okay, and it's saying, okay, this is an answer that this student answered that question, right? And it's also a mixture of normalized and denormalized, right? In this case, it's normalized because I'm pointing to the references, right, of the students in question. But I am denormalizing the fact that I'm maintaining the answers for all different types of questions. Right? If this question was a multiple choice question, then this is my answer for that question, right? And then the true false would be null. That I'll have because it is a multiple choice question, right? So I have an answer for the multiple choice. If this were instead a true false question, then I would have an answer for this, whereas this would be null. Right? Now, but the difference here is that in the relational database, there would be a null, right? You would one of the complaints from DBAs. When we use denormalized schemas, is that you typically, if you look at those tables, there's tons and tons of empty space. You have nulls and nulls everywhere, okay? And DBAs hate that, right? Of having all this empty space, nulls everywhere, okay? Here we don't have that problem, right? Because if we have value for multiple choice answer, right? It's not like we're going to have an empty space for the true false. It's just not going to be there. It's just not it's not even going to show. Right? So it's not going to show like lots of nulls everywhere if we don't have a value for that, right? So in that case, it's a good choice. All right, so we're also going to implement some Mongoose model. So Mongoose is going to be the library that we're going to use to programmatically connect to the database, right? It's what's going to. It's the equivalent of JDBC or JPA, right? Now, if you remember, JDBC was a very low, a low-level library, right? That talks to the database in its native language, SQL, right? And then on top of that, we added JPA, which was a higher-level library that allowed us to talk about the database in object terms. Yes. So Mongoose is kind of the equivalent of that, right? It's built on top of the native MongoDB driver. Right? The native MongoDB driver is bare bones, right? It doesn't do a lot of validation. It does, it allows you to talk to the collections directly and whatnot. Mongoose builds on top of that and allows us to add validation, allows us to do some making sure we don't have SQL injection or we don't have any does higher level data type validation and object validation for us. Okay, so the models in Mongoose are the equivalent of the repositories in JPA. Right? Remember, the repositories in JPA gave us some native implementation of some CRUD operators. Remember that? Right? The finders, the deletes, the save, the several finders. What else? Updates, right? We had some implementation of some native implementation that allows us to interact with a relational database. Here, Mongoose models allow us to do the same thing. It will give us the commands that will allow us to interact programmatically with the database. We'll create some DAOs. So these DAOs are kind of the equivalent of DAOs in relational database when we implemented DAOs in using Java, right? Basically, they are it's a good practice, right? It's a best practice to encapsulate or modularize any database interaction, right? And provide a high-level interface for the rest of the application, right? To interact with the idiosyncrasies of the actual database, right? We do ask you to create the following commands that allow for finding all the students, find a student by ID, finding all the questions, delete an answer, finding all the generate a brand new answer, delete a question and whatnot. Right. So all the lifecycle functions that allow us to create questions, answer, and whatnot. Okay. Finally, so here's an example of putting all these functions inside of one single DAO, the university DAO server. So one of the first things that we'll ask you to do is to create what is called a populate database function. This populate database function is going to generate the following data in your database. So it'll create 2 students, Alice and Bob. It'll create 4 different questions, 2 true and false and 2 multiple choice. It'll create several answers by Alice and Bob. So you're going to create in your DAOs, you'll create all the commands that would generate all this data in the database, right? And then you'll create a test suite, right? That's going to validate that all the data is in there, right? And ideally, the TA should be able to just do a node space test.js. It runs the whole thing, and as it prints out, you should be able to validate that everything worked correctly. And your test suite should first truncate the database, meaning drop everything, right? Empty the database so there's no data. And then we're going to populate it. We're going to insert lots of data, and all the students, the questions, the answers, and then we're going to check to see that the student count is correct, the question count is correct, the answer question is correct. We're going to delete an answer. We're going to delete a question. We're going to delete students and verify that all that is working. I think that's it. Yeah. All right. Yes. Yes, in Java. Yeah, no JS. And you don't have to actually use a test suite. It's just a called test.js. So you don't have to use like Karma or some of these unit All right.